So I set up this differential equation for the transient RLC circuit. I want I as a function of time. What do I do? Where do I go from here? I have I's and Q's. I have two options. Okay? I can write I in terms of Q, because isn't I dq dt?
Mm-hmm.
And isn't di dt the second derivative of Q respect to time?
Mm-hmm.
So I can solve for Q and then take the derivative of that and get the current. I can do that. That's fine. I'm not going to do that though. I'm going to take the derivative of this whole differential equation.
Is Q the charge on the capacitor?
Right. And so now when we take the derivative, we get the following. dq dt and what's dq dt? I.
What was that to the left of dq dt?
1 over c.
Okay.
Okay, let me rewrite this. Let me go, let's see, I forgot the minus signs here. I'm going to multiply through by -1. I'm going to write it down over here. Let me divide both sides. Let me divide by L. Okay? I'm going to divide by L. This is this is called a homogeneous second order differential equation. And like I said before, I know that I equals 0 at t equals 0 and I equals 0 at t equals infinity. And I got to solve this, but I haven't had math 33. And I know there's going to be some sort of exponential function involved. And solving a differential equation basically is like integrating some function twice. So somehow I got to get two constants of integration when I solve this. So I'm going to guess the solution. I'm going to guess the following. I'm going to guess this function. Where a is a constant, okay, and omega is something that depends on these terms. Okay? And guess what I'm going to do next?
What does that omega stand for? Or are these all just like...
We'll find out. I mean, it's going to depend on time. So omega is going to have units of 1 over time, right? I have to have something. I can't just have time here. Some constant that has units of 1 over time.
Oh, okay.
So Chase, if you take the derivative of the battery voltage with respect to time, it's 0, right? Because it's constant. Okay. So I want to substitute this into the differential equation. We're actually doing math now. What's nice about the exponential function is when you take the derivative, you get the same function back times constants, right? So isn't it true that when I take the derivative of this, I'm going to get the following? And then for this one, nothing changes. And then for this one, I'm going to get that look okay so far? And I'm going to factor the a e to the omega t out. In order for this to always be 0, for any value of time, the thing in the brackets has to be 0.
Oh, you're missing an omega. In the very left. The R over L.
You're right.
Have an
Thank
omega.
you. Oops, I'll do it that way. Okay, so what I need then is this to be true. So I need this to be true for all anytime. So that's going to establish what omega is. Okay. What's omega? Well, to figure out omega, I have to use the quadratic formula. Did I drop a sign? Did I drop something? No, we're okay. Never mind.
Should that be minus R over L?
Yes, thank you. Minus R over L plus or minus R over L squared minus 4 so I'm going to get the following. And I'm going to put this inside the root. So that's the condition in omega. And it turns out that there's 3 possibilities for my omega because of this term.
And a minus in front.
I'm sorry?
There's a minus in front.
Oh, geez. Sorry. There's 2 values of omega, but there's 3 possibilities for each of those 2 values. So my solution, so there's 2 values of omega. That means my solution has to look like this. And this is nice because now I get my two constants of integration. That's my solution. Now, I forgot a 2 here, didn't I? I can factor this term out, and I get the following. Okay, but the thing under the radical is what's interesting, because we can have r over 2l minus 1 over LC be bigger than 0. We can have this difference be equal to 0, or we can have this difference be less than 0. So the solution I get is going to depend on what this is. Does that make sense?
Mm-hmm.
So let's look at the case where this is bigger than this. So you see there's a lot of writing on the board today. Let's look at the case What does that mean? What does it say about the radical?
Positive number into the square root.
Yeah, so this is positive, this is positive. What do I get then? What does my function look like? This is called underdamped. Well, you have, in fact, this exponent, the concern here is that this exponent is positive, right?
Mm-hmm.
But this exponent is less positive than that is negative, correct?
Mm-hmm.
And this times this gives you a negative exponent. And so basically what you have is some sort of decaying exponential. The current goes to 0 and it decays exponentially without an oscillation. So if you plot I versus t in this particular case, it kind of does this. Okay, so we call that underdamped.
Can you go over how it first increased?
It's because of this term.
So that was less positive than the one on the outside. The exponent.
Yeah. Actually, I didn't say it, I meant overdamped. Hold on a second. Yeah, in order for me to go through the details, I'd have to solve for A and B, which I'm not willing to do right now.
Okay.
Okay. All right. The next case, which is of more interest, is the case when this is less than this.
So now we are imagining things.
Yeah, now we're imagining things.
So I haven't taken differential equations yet, and I'm like really lost in all of
I'm
this.
not doing math 33 here. Right? I just guessed the solution. Right? So I'm not doing anything really beyond the scope of the class. Where are you lost at?
Well, like I guess at the point where there were like dt squares and stuff like that, and then I just don't really understand like what the whole concept of like guessing the equation was.
Well, isn't it true that I can use intuition to solve a problem? We do it in physics, right?
Yeah.
So why can't I do it in math?
I don't know. I'm just
Basically, in Math 33, there's like certain types of differential equations you can solve using like these different functions that you plug into the equation, and that's what he did. He just like quote unquote guessed the correct one to use.
Yeah, I just guess.
But there's nothing really special about it.
Yeah, I mean, I'm just guessing the solution because I know that the solution is going to be exponential. In Math 33, you do it more general in a more general way. I can't do that here.
I think that might be helpful to think that if you look at the equation, you have the di dt and the d2i dt2 both positive. And like, what is a function whose first derivative and second derivative is the same? That is like the exponential, it doesn't change sign. But if the signs were opposite, you would have guessed sine or cosine to do that. Maybe
That's right. That's right. So there's a question, could I have guessed a different solution equation? Kathleen, yeah, I probably could have guessed a different equation, but I probably wouldn't get anywhere.
So I guess I'm concerned. I mean, other than the fact that I'll probably have to take differential equations eventually, I guess the main thing that's concerning me is like, will we need to like show all of this, like guessing the function and all that on the lab, like on the?
No, because there's no theory part for this lab for part 3.
Oh, okay. So we can take whatever you end up with and use that for the lab.
Yeah. However, when you take physics 215, and you'll probably do a driven Dant harmonic oscillator, you will solve a second order differential equation, and you will have to write it in your lab report. But the thing is, you're guessing a function. I'm not using Math 33. Okay. I'm using my intuition. That's all I'm doing. It's like, I mean, look, let me do this for you, because I want to do this in class today. Okay. Can you tell me what the solution to that is, Vincent?
I think what's throwing me off is the square after the d. Like it makes it look like it's like a distance or something. Does that just mean?
How about that?
Well, I mean on the left side of the equation, there's like, is that dx squared, or is it
d2x dt squared, right? Second. That's why you write the second derivative.
Oh, that's a second derivative. Okay.
Right. So, how do you solve that? Can you tell me the solution? Actually, can you tell me the answer to that? I bet you. If I want to tell you one thing, I bet you can figure it out. Right? It looks intimidating to you right now, right?
Yeah.
Okay, what function I can take the derivative twice and get the same function back?
It's e to something. I remember that
With the
from
minus sign in front. What's the derivative of sine?
cosine,
What's the derivative of cosine?
negative sine.
There you go. Sinusoidal function. So it's basically, you got to know your trig functions, right? Right. I mean, this is something that we do in this course, and you don't have to know Math 33. You know, we just use intuition that the solution to this is sines and cosines. The omega, just a constant that comes out when you differentiate. Okay? So let's look at the case where...
This sounds like vaguely familiar from like what I did in Calc 3, but I mean, like, I don't remember a lot of that course.
This is not Calc 3 though. There's nothing
Really?
in what I did here is Calc 2 or, Calc 3 or DE. Right? I mean, I'm just... You know what the derivatives, you know what the derivatives of sines and cosines are, right?
Yeah.
You know that if you differentiate a sine function twice, you get the sine function times a minus 1. You know that if you take the derivative of the cosine function, you get the cosine, if you take the derivative of the cosine function twice, you get the cosine function times minus 1. Maybe some other constant involved. Isn't that true?
Yeah.
So just use your knowledge of that. Right?
Okay.
We're not using a procedure, you're just using your intuition, stuff that we know already. And that's what I'm doing here in solving this. I know that's why I started the class saying, I know the solution is going to be 0 at t equals 0. I know the solution is going to be 0 at t equals infinity. And I know it has going to be some sort of decaying exponential in it. That's why I guess an exponential function. Okay? I am not doing Math 33. I'm just using my ability to solve the problem. I mean, you're going to see later in class today, I'm going to have the second order differential equation that I wrote up a second ago, and I'm going to tell you what the solution is. Okay? And 215, you're going to see the same thing. So what happens if this exponent is negative? Then I'm going to get the following. I can't leave it like this. This is negative. What's the square root of a negative number? What's the square root of negative 1?
I.
So I'm going to write it like this. Okay. And I know you see this in Math 33, but I know you've seen it somewhere else. What does this mean? Now I get silence. What does this mean? Anybody know what Euler's formula is?
Yeah.
What's Euler's formula?
It's e to the IAB or something like that.
Well, what is that equal to?
Oh, yeah.
Have you folks seen that before?
Yeah.
Anybody else seen that before? No. Okay, so if you take math 31, sorry, and you expand this in a series, you'll get this. Okay, in math 32, because in math 32 you learn how to expand these functions, right? See, when I learned this, I learned this in pre-calc a long time ago. So when you expand this, I mean, I learned this function in pre-calc. I didn't do the expansion in pre-calc, but when I took the equivalent of math 31, sorry, calc 2, I learned how to derive this. Right? Isn't e to the x 1 plus x squared plus x squared over 2, right? Isn't that the case? Have you ever done that with the exponential function?
Mm-hmm.
No? Only one person saying yes? Anyway, if you expand it, you get this thing. So these are sines and cosines.
I think for the e to the x it was 2 factorial and then
2
3
factorial. Yeah, I don't remember. I'm just.
Okay.
But I mean, the thing is if you expand e to the x, and you make the exponent imaginary, you get sines and cosines. And so this ends up being the following. We can write it in the following way. What does this look like? What does that function look like? You have a sine function with a decaying exponential in front of it. What does that look like?
The magnitude of sine decreasing, like the amplitude.
The amplitude is decreasing. I'm going to have a hard time plotting this. Looks like that. So this is called underdamped. The current oscillates to 0. And you see this in circuits, and in some circuits, you don't want this. This is called ringing. You don't want ringing in circuits. So what you're going to do in the lab, you're going to choose R, L, and C so that you satisfy this equation. So you're going to choose R, L, and C so that this is true. You get to choose from your kit, okay? You choose from your kit what values of R, L, and C you use to observe this. Hook it up. Observe the signal on the scope. Look at the signal across the resistor. You can do the inductor too, but let's say you look at the signal across the resistor. Okay? Take a picture of it. I mean, not take a picture, but yeah, take a picture of it and put it in your lab report. That's it. That's all I want you to do. I want you to build a circuit with a resistor, a capacitor, and an inductor. Of the right values, so you get the ringing. And I showed you last week what it looks like. Hold on a second. Let me open up the a file. I had it open last week. Just 1 second. Yeah, go ahead, Chase, while I'm trying to get this thing working. If that's not what I want. So, do you guys see
Yeah.
the traces? So basically all I want is a picture that looks like that, especially the one at the bottom. The bottom right. If you can get that one, that'd be great. Just look at the voltage across the resistor. I'm sorry, yeah, look at the signal across the resistor. Because that's going to be indicative of the current, right? Because I is V over R. And see if you can get that. But you put in a square pulse, okay? Put in a square pulse. Because otherwise, if you don't put in a square pulse, you won't be able to see anything. So put in a square pulse into your RLC circuit and measure the voltage across the resistor. Okay? So some of these look bad, right? I mean, the ones in the upper row, the ones on the left are fine, and the one on the bottom is fine also. Those are okay. Okay, all the other ones are garbage. Wow, the one in the second row, the first one in the second row has very little ringing. So that's an underdamped circuit. And so what I want for you is to give me an example of that. Okay, take a picture with your scope. Tell me what values of R, L, and C you use. You don't have too many choices. Okay. But the thing is that
Do you want like 5 clean oscillations that are visible on the scope or something like that, or?
that one has a lot. I mean, if you can get 5, that'd be great. If you get 2 or 3, that's fine. Okay, it doesn't have to be 5. The number of oscillations you see is going to depend on this, but also on how many values of R, L, and C you have. So you don't have a lot. Okay. And I did hide the values. That's why there's that dark mic, that dark line across, so you won't see the values. Because I want you to calculate based on the values you have. You want to satisfy this condition. So Chase, you had a question?
Yeah, I have a question.
Go ahead.
On the lab, it says when you're doing the RL circuit, it says the amplitude approximately 1 volt as measured with the scope. What does that mean?
You're talking about the last lab?
The one we're doing, the transient lab. What does it mean for the amplitude to be 1 volt? Is that V max?
Yeah, I mean, Yeah, it's really more than the amplitude. I want this whole thing to be 1 volt.
So it's not the volts per division, right? That can be whatever you want, like
Yeah,
to get
yeah.
a
You
good
just
reading.
you want the voltage to be 1 volt going in.
So we use that little knob on the signal generator, right?
Correct.
Okay.
What did you do in the first part?
Well, I hadn't got to yet because I was confused on that,
Okay.
but I got it working like after I made that mistake.
Yeah, I mean, your signal looks like this. Basically, I just want this to be 1 volt. Okay, that's it. So if it's on 1 volt per division, this is one box tall. The reason why I limit it to 1 volt is that darn signal generator can't drive enough current. Otherwise, I would have you choose the voltage. Okay?
Wait, so this is the volts per division has to be 1 volt, right?
No, it doesn't have to be 1 volt. It can be whatever you want. It's the voltage
Okay.
of the, right? The number of volts this signal is, right? It doesn't matter how you measure it, right? I can have it on a 0.5 volt per division. That makes this two boxes tall.
Yeah, okay. I see now.
Okay. Okay, so is there another question on the lab?
I had a quick question. So, like, when you say like choose values of R, L, and C, you mean like the physical parts of the circuit, right?
Yeah, well, the components you're going to have in your circuit, right?
Oh, okay.
I mean, you're going to have an R, L, and a C. Where are you going to get them from? Your kit, right?
Yeah.
Okay.
So there can only be like one kind of setup you can do, right? Because we only have one kind of inductor.
Don't you have 2?
Oh, we have 2. Are they different?
Yeah, one's 1 millihenry and the other one's 10.
Okay.
Right, the smaller size one is 10 millihenries. The bigger size one is 1 millihenry. It's bizarre, but you think it'd be the other way around. So you have 2 choices for L. I forget how many choices you have for C. And then you have a lot of choices for R. You even have a 1 ohm resistor in your kit. Okay. So I want you to think. I want you to figure out what works for you. I don't want to just tell you what to do and then you do it. You're not going to learn anything from that. Okay. I want you to figure out the right values of R, L, and C so that you get the damped, underdamped circuit. There's one more case though, right? I haven't gotten to the one more case. Can I just say something about the last case? The last case is when this is true. If they're equal, then what? What happens if these 2 are equal?
Just simple exponential.
Yeah, this is, in fact, you get the same thing, right? Because the square root is what?
0.
0.
Will just be like some constant times the outside exponential function.
Yeah, you're gonna have A like that. It turns out that you really need 2 solutions. You have to have 2 solutions, right? Because when you solve a second order differential equation, it's like integrating twice. Unique two constants of integration. So this is where I have to just tell you something. You have to believe me, okay? You can find a second solution. And it looks like that. Okay? So one can show that the second solution there's a trick you have to do. Now that part's math 33. Okay? So this is called critically damped. So the system goes to zero in the shortest time possible. Okay? So let me show you examples. Let me show you graphs of these. Let me open up my PowerPoint. These graphs are in your PowerPoint notes. This is what the three graphs look like. So in one case, the red one is the one you're trying to get, the underdamped one. The critically damped one goes to zero in the shortest time possible. And then the overdamped reaches steady state with no oscillations. Now you can, if you want, you can solve for Q. You can integrate I to get Q. And the Q equation looks like this. This is the charge on the capacitor is a function of time, or the voltage on the capacitor is a function of time. It looks like that. Okay. Those of you who took 215, have you seen this before?
Yeah.
Because this occurs when you have a mass on a spring. Same math, exactly the same math. Okay? If you ever want to talk about how shock absorbers work, you don't want underdamped shock absorbers. Because when you hit a pothole, you're going to be bouncing forever. Okay? So the math here applies not only to the circuit we see here, but also to what's called a damped harmonic oscillator. Okay? So all you need to do for the last part is choose the right value of R, L, and C so that you get an underdamped circuit. That's it. That's all I'm asking for. Okay? Questions on that?
I think on the previous slide where you have the overdamped and the critically damped and the other oscillation.
Yeah.
I think the graph that you drew on the board for overdamped is actually for critically damped.
Yeah, well, I mean, it just depends. I mean, it depends on the values of R, L, and C you use, right?
Mm-hmm.
So I chose, when I plotted this in Capstone, I just chose R, L, and C, the same R, L, and C to give me those graphs. And it's possible that the critically damped version of what I drew can go to zero a lot faster, right? Depending on the value of R, L, and C I'm given.
So
That's all. So it's hard to say that. It's hard to make that conclusion.
yeah, so the overdamped for the one that we see right now, it goes to zero much later in time.
Right. But
Okay.
but that depends on the values of R, L, and C, right? Okay, so it's hard to say that that what I drew is the critically damped because you didn't see the other version.
So is it also hard to tell on the scope whether something is critically or overdamped?
Yeah, you have to compare them. Right.
So the one for which the time is less, that is critically damped.
Yes.
Okay.
Yeah. I mean, suppose I mean, I can have. I mean, I can have these cases. Right, or I can have the values of R, L, and C, so it does this. I mean, there's not a big difference, right? I can also have a value of R, L, and C where but you know what I mean, though. Okay, so what I drew earlier in the class, it could be. It just depends on the values of R, L, and C. That's all.
Yeah.
So if I would have driven the critically damped one, it would have gone down faster. That's all.
Yeah.
So yeah, it's hard to make that conclusion. Okay. Questions on this? So on the lab, again, all you need to do is to demonstrate an underdamped circuit. And no, I'm not going to have you solve problems like this. Okay. I know that Harris does give a worksheet on this problem. I do remember him. He does that. But I'm not going to do that. We don't have time to go through that. Have you guys do a worksheet where you guess the solution. When you take Math 33, you'll solve a lot of these problems. And you'll probably do this in Engineering 17B. But by then you would have had Math 33. Okay. They're fun problems. Okay. Other questions? Because I want to talk about the last lab. We need to talk about the last lab. I only got a few minutes left. Okay. The last lab we will be doing is an RLC lab. And yes, next week, I will also solve a differential equation by guessing. So it might not be very appealing to those of you who don't like me to go through the math, but we have to do it. Okay. But I will also solve it a different way in class. So you will see the solution to different ways to this problem. So we're going to look at this circuit, but we're not going to use a square wave, and we're not going to use a battery. We're going to drive it with a sine wave. We're going to use an input that's AC. It's not until Tuesday where I will go through the theory. This is a very complicated lab because we're doing AC. And yes, I can set up the differential equation for this. And I will do it next week. And this one's even more complicated because you actually get two sets of solutions. One is a transient solution, and then the other one is the steady state solution. So I'll talk about the steady state solution next week. Okay. But in class, I'm going to show you a completely different technique to come up with the answers. It's much faster. But it's nicest for you to see it both ways. And then when you take DE, you'll say, oh, I've seen that before. Okay. So we're gonna learn this circuit inside out. We're going to analyze almost everything in this circuit. If you were on campus, you would analyze everything in the circuit. Okay. Our goal is to get a graph of the current as a function of frequency for that circuit. Okay. So I'm going to write down the procedure. Wire the circuit. Okay. Then measure and record the ammeter resistance on the 200 milliamp scale. You have to use a 200 milliamp scale for this lab. The whole time, cannot change. Okay, why do you want to know this? Because it's going to affect your circuit. Here's the problem with the lab. When we do this on campus, okay, we use 5 multimeters at the same time. You have 1. Okay? Or maybe it's 4 multimeters at the same time, I forget. 4 or 5 multimeters at the same time we use. I think it's 5. Okay, but you have 1. So that's what's going to make this lab a pain for you, because you get to take the multimeter and move it from place to place. So that's what makes it more time consuming. Okay. Set the signal generator. To 1 volt peak to peak. What do I mean by that? That's what I want, 1 volt peak to peak. Why do I want 1 volt peak to peak? Because of the fact that if you put too much voltage, you're going to, the signal generator cannot drive the circuit. And you're going to use the scope to monitor the voltage as the frequency is varied. Okay. You're going to have to adjust you're going to have to adjust the voltage to maintain the same 1 volt peak to peak voltage, because when you change the frequency, this voltage will change, okay? Because our signal generator isn't that great. Okay, next. I'm writing this down so that you have a record of it. So if you have a question, I will say watch the video. Place ammeter in circuit. To measure the current, AC current. You got to use the big multimeter. You cannot use the small one. Forget the small one, okay? The small one is not going to be good for you in this lab. Do you guys know where the AC settings are on this thing?
Isn't it the little squiggly line?
Yeah, so it's all the orange stuff, right? Good. You know, everything that's in orange is AC. And the multimeter doesn't measure instantaneous voltage or current. It measures some sort of average, which we will discuss in lecture. Okay. All right. Now, find frequency where I is maximized. See, this graph is going to look like this. You want to find a frequency in which is maximized. And then you're going to compare to one over 2 pi times LC to the negative a half. Okay? Then find, so while you're at this frequency, we're going to call this FRES, okay, which will tell you, well, I'll tell you what that means later. Okay.
Is that a negative 1/2?
Yes, it's a negative 1/2.
Oh, okay.
Okay, find the smallest change in frequency from FRES such that the current changes by, let's say, 0.05 to 0.08 amps. And this will be your step size. This will tell you it's the shortest, the smallest interval you can use in your experiment. You're going to actually measure as a function of frequency, right? But you need to know how much you can change the frequency. So you need to figure out what is the smallest step size you can use, because you need to use very small step sizes up here, okay, so that you can pin down the peak of this graph, because you're going to do a curve fit to that thing, okay? So, and hear me out on this one, this is important. If you're at the resonance frequency and the voltage on the signal generator gets distorted, then reduce this voltage. And this is going to be an issue, this is a problem with the signal generator. So if you get to the resonance frequency and your scope signal looks distorted, reduce this to, go to 0.9, then 0.8. You just lower it until the signal's not distorted anymore. And you will work with that voltage. Okay, that's important because otherwise it's going to mess up your whole lab. Okay. Once you've done all this, then set F equals 200 hertz. And measure and record I. So your smallest value will be at 200 hertz. And then your largest frequency is 2000 hertz. You're going to go from 200 to 2000 hertz. I'll say that again. You will scan from 200 to 2000 hertz. What's your step size? Do you want to go by tens from 200 to 2000? Should I tell you yes? You guys still there?
Yeah.
Okay. Okay. So your step size is going to vary. Your smallest step size is here, but over here your step size may be 200, but here might be 10 hertz. That's why you need to know that you need to go through this. Remove ammeter and measure V sub L, V sub C, measure the voltage across the inductor, measure the voltage across the capacitor, and it's optional if you want to measure the voltage across the resistor. Okay? This is for troubleshooting purposes, so you might want to measure. You're not going to do anything with it, but for troubleshooting purposes, you might want it. So here's the thing. You got to put this in the circuit, take it out, and then measure the voltage across the inductor, the capacitor, and if you want the resistor, the same multimeter. So that's what makes this painful. Okay. Make sure you know the resistance of your inductor. Make sure you know the resistance of your inductor. So once you've done this, then go back and change the frequency and just keep doing it until you've gone all the way to 2000 hertz. And then what we're going to do is we're going to use an Excel spreadsheet to calculate everything. You know, Kathleen, it's a good question. It is less accurate. You know why? Because of this. The ammeter has resistance, and you're changing the circuit every time you put it in and out. Oh, I forgot to tell you the resistor you're going to be using. I'm way over time, but let's see if I can get real close. Oops. This is the resistor. It's gray. It's 1 ohm. Okay, the resistor you'll be using is 1 ohm. It's gray in your kit. Okay. There we get, if I get any closer. Can you guys see that?
Yeah.
Okay. So that's the resistor you want to use, or you're going to use. Okay. The inductor is 10 millihenries, and the capacitor is 4.7 microfarads. So next week, when we talk about the experiment, I'm going to talk about how to graph it. I'm going to talk about what information you're going to get out of it. If I don't have time to solve the second order differential equation, I have a video already for which I did it. I have 3 videos on this. So if I don't have time to solve the differential equation and go through some of the theory, I have videos on it. So you'll have to watch. Okay, so what I'm trying to do is not meet the last week of the semester. Okay, so because like next week hopefully is our last meeting for lab. Okay? All right, so I'll see you guys. I got to run to my 9:30 class.
Thank you.
All right.